Okay, good morning everyone, and welcome. Today I will share with you a new digital discovery paradigm that combines synergistically many GPU high-performance computing, AI, and advanced computational quantum mechanics to accelerate and transform molecular discovery across chemistry, biology, and material science. So we are going to combine all of these technologies together. I will discuss what are the breakthroughs that are making this possible and how this new digital discovery paradigm it is incorporated, optimized, and utilized by QDX technologies in collaboration with some preeminent drug discovery companies across the world to accelerate the creation of novel therapeutics and enable the rational design of treatment for diseases that are currently incurable. So if you're looking for a roadmap to harness high-performance computing, AI, and quantum mechanics for real-world impact, you are in the right place. Today, there are many scientific problems of key technological and societal importance that cannot be efficiently tackled using computers or experimentation alone. And some of these problems are on the slide there. They span from the discovery and design of novel therapeutics and enzymes to that of novel catalysts and materials and metamaterials with properties that do not normally occur in nature. Now, for these problems, traditional physical experimentation, although invaluable, is often hindered by slow turnaround times, high costs, and the inherent limitations of physical synthesis and observation. So you might not even have necessarily, for some of these cases, reliable characterization techniques from an experimental perspective. Now, from a computational perspective instead, the common challenge of these problems is that their resolution requires accurate molecular simulations and characterization for large atomistic models, including thousands of atoms in a complex environment, such as in solution with multiple components. Unfortunately, at large molecular scales, simulations have been either inaccurate and fast, or accurate but too slow for the resolution of some of these problems. Among these problems, the discovery of novel therapeutics is particularly close to my heart and to the mission of QDX technologies. This is an incredibly inefficient area of technology where developing a new drug takes over a decade, costs us billions of dollars to be successful in clinical trials only 12% of the time. Despite this huge investment, 80% of the proteome currently cannot be drugged using traditional non-covalent therapeutics. This leaves diseases like Alzheimer's, certain cancers, multi-drug resistant infections largely incurable, and these diseases affect 75 million people globally and kill 13.5 million people every year. This is a catastrophic toll taken on humanity. Covalent therapeutics, which are novel kinds of therapeutics that form an irreversible bond with their proteins, can target these undruggable proteins. And some of the work that you will see today paves the way for the first accurate in silico software technology for the design of covalent therapeutics. When we talk about drug design here, we refer mainly to the preclinical design. As probably most of you already know, when we have a disease, typically responsible for that disease is a malfunction or a mutation in a protein. We then design a chemical, the therapeutic, that binds at a specific point of that protein to modulate or inhibit that particular harmful function. So how is this achieved? Well, it is an intrinsically multi-stage process. Typically, we start with a virtual screening and design phase, where instead of physically testing in the lab whether compounds bind to the protein, we take our candidate protein structure and libraries of, with inside of them, literally billions of drug-like molecules, and feed them to a simulation pipeline which screens these candidates with increasingly accurate and increasingly computationally demanding models of this binding. At the top of the funnel there on the slide, we have models that are typically quite crude. They may test for structural compatibility or similarity to existing therapeutics. Then we have molecular docking, which is binding models that are quite approximate in terms of the physics that they use. Or these days, for example, even in QDX, we use deep learning docking models, so based on AI. Then finally, we get to molecular simulations. So these are also approximated because they use classical mechanics. And drug binding is an intrinsically quantum phenomenon because electrons are involved. So at that point, we can study how changing the molecular structure changes the binding in virtual quantitative activity relationship study. I change a functional group, I obtain this different activity. So by the end of this funnel, ideally we have some good candidates. We have screened from billions to thousands, and we need to test them. So in parallel, we will have to build a binding assay, and this can take up to a couple of years, cost us a couple of millions of dollars. Then we can test this binding in vitro. So if we wanted to test millions of candidates without undergoing this virtual screening process, this will cost an astronomical amount of money. Notwithstanding that, many companies today, many big pharma companies today still do that because they can. After testing, ideally, we find some compounds that bind, and that's when actually the game starts. We give these compounds to humans, and these humans are going to modify them over many cycles that take many years and many millions of dollars to optimize for certain properties, for example, binding. Now, obviously, from the perspective of the costs and the development time, what we really would like to have is that we take our hits from the virtual screening and then synthesize them, send them to the lab, and the predictions perfectly correlate with the experiments, so we don't have to run many cycles. Ideally, we don't even have to run any optimization on these compounds. And this doesn't really happen, right? So today, the average drug discovery company is trapped in many cycles of simulation, experimentation, and optimization. And that's why we waste all this time and money. Well, it's not wasted, but why we use all this time and money to develop a new drug. Well, the reason why this doesn't happen, though, is that our simulations are not sufficiently accurate. They do not correlate sufficiently well with the experiments. For example, the vast majority of molecular dynamics simulations today rely on classical potentials, which treat atoms as classical particles and molecular interactions using empirical models. While these models are computationally fast, they fail to capture with sufficient accuracy non-covalent interactions that are critical for the energetics of biosystems. In fact, biosystems are driven by non-covalent interactions. Furthermore, these methods are limited in what they can simulate. For example, they cannot simulate at all reactions, which, for example, exclude the idea of designing covalent therapeutics. These inaccuracies ultimately lead to this lack of reliability and correlation with experiments, as seen here for these data charts of binding affinities for non-covalent therapeutics in drug discovery. So in each one of these data charts, one data chart is a protein, all the points are different ligands, and we are measuring the correlation between the predictions and the experiments. And as you can see, they do not look great in many cases. However, it's been long known that if we were able to solve the Schrödinger equation in quantum mechanics, we could predict any property of any molecular system with very high accuracy. Ab initio quantum chemistry methods, such as the MP2 method that I will discuss later, solve this equation numerically without using any empirical parameters. Now, these methods can provide an accuracy that rivals, or in some cases, surpasses physical experimentation. However, this comes at a very steep computational cost that makes their application, has made their application historically confined to small molecular systems. So no big proteins, no drugs. This slide shows the comparison of accuracy between for the same binding affinities as before, when using quantum potentials to calculate those drug binding affinities. The improvement in correlation with experimental data is both qualitative and quantitative. For instance, if you look in terms of classical potentials to the prediction for binding affinities represented by the yellow data, you will see that they exhibit a negative correlation with experiments. Where instead the quantum potentials align closely with the experimental results, demonstrating significantly higher accuracy, but ultimately that if you had used quantum potentials, you would have made the right choices for the design of your therapeutics. Furthermore, quantum potentials allow naturally to model reactions, granting us access to covalent binders, which are very much of interest for QDX as well. So what's the state of these quantum chemical calculations? At the petascale level, we could perform relatively accurate calculations on systems, molecules with less than 1,000 atoms. A few years back during the exascale computing project, we postulated that if we were able to use an entire exascale machine, we might be able to push these calculations to systems with hundreds of thousands of atoms, which is exciting because it gives us access to the bioscale. I used the conditional here because there are some major challenges along the way of enabling these quantum chemistry capabilities. The first one is a well-known one. Solving the Schrödinger equation with sufficient accuracy scales as a very high power of the number of atoms n within a molecular system. And the table there on the slide shows the scaling of quantum chemistry methods in increasing order of accuracy and computational cost, top to bottom. Now, in general, the energetics of biochemical systems, as I mentioned earlier, is driven by non-covalent interactions, such as hydrogen bonding, pi stacking, and other van der Waals interactions, which is where hybrid density functional theory, for those who are familiar with these levels of theory, fails to deliver the required accuracy. So we need to go beyond this hybrid DFT level at the level that I call PT2, which stands for second-order perturbation theory. It's in reality a set of theories. However, this scale as order n to the fifth with system size. Now, this has historically confined the application of these techniques to small systems, especially when you do simulations. And if you look at the bar chart on the right-hand side, that shows the maximum system size achieved in molecular simulations at those levels of theory together with the error associated with them. And you can see that MP2, before our simulations, was confined to 140. The largest calculation was on 140 water molecules. Other challenges, beside the high computational cost, we also require dynamic simulations rather than simple static energy calculations to be able to obtain statistically meaningful predictions on macroscopic properties. This requires not just energy calculations, but much more complicated quantum mechanical gradients to be able to run in general multiple and many time steps. And the last challenge is associated with the inability of many of these quantum chemistry codes and in general legacy codes in scientific computing to efficiently exploit novel, massively parallel hardware. This is due to the fact that many of the theories and the underpinning algorithms were designed during the 80s and the 90s for latency-oriented architectures, so the old good single-core CPUs, and they are typically unable today to efficiently exploit the massive parallelism of GPUs or exascale generation hardware. In general, of course, beyond that, using a machine like Frontier at scale is challenging for any application. as it requires exposing massive parallelism and very sophisticated algorithms. Each GPU on this machine has 14,000 cores. There are 4 GPUs on each node, and there are 9,408 such nodes on this machine. So if we want to enable these capabilities, we need to start from scratch. We need to redesign the methods, the algorithms, and the implementations so that they have a reduced computational complexity, so they can scale, for example, from order n to the 5th to linear, while retaining the required level of accuracy, and that are jointly designed to efficiently exploit the massive parallelism of exascale generation hardware. And these were the founding principles of the extreme scale electronic structure system, which was our software package, which was designed from the ground up to deliver this scalability and accuracy. Now, a few more technical slides here to explain a bit how we achieve lower scaling and massive parallelism in excess. We use a molecular fragmentation approach whereby we take a molecular system, we break it into fragments called the monomers, and then the energy of the overall system is recovered hierarchically using this many-body expansion up here as a sum of energies of monomers, these EIs, and higher order terms which involve pairs of monomers called dimers and triplets of monomers called trimers and so on and so forth. Now, one big advantage of this is that it's a massively parallel approach whereby I can take a polymer, each polymer, and map their calculation to a group of nodes. This doesn't solve the exascale challenge. You still will need to redesign all the underlying calculations to run efficiently on a GPU cluster. Then the second important advantage is that this approach can be made linear scaling. So as you see on the slide, I show an order nm, where nm is the number of monomers. This scales only linearly with the system size. So we go from quintically to linear. How is this achieved? Well, the magnitude of these 2-body and 3-body corrections here in our MBE, this delta EIJ and delta EIJK, decays very quickly with the distance between the composing monomers. So this allows us to systematically consider only dimers and trimers whose monomers are spatially close, specifically there within a radial cutoff called R-cut. A big difference with previous approaches in this area is that we screen these interactions rigorously by looking at the energy contributions of the corrections and consider all the dimers and trimers whose corrections are above an accuracy threshold of 0.1 kilojoules per mole, which is a tiny amount of energy, leading to no loss of significant accuracy. And this is shown on the figure there, which shows the magnitude of these dimer and trimer corrections with respect to the distance and how we obtain the cutoff using the 0.1 threshold, 0.1 kilojoules per mole threshold. So if we stop the 5 angstroms, obviously there would be no point on running accurate MP2 calculations because the error of this approach will be huge. Here I'm just showing that we go up to trimers, so 3-body corrections. You don't need to understand those formulae. The key thing is that the energy is the sum of these R3 and MP2, so we go up to the PT2 level. This scales as order n to the 5th, but now this order n to the 5th is with respect to NF, which is the number of atoms within a single fragment. So that doesn't scale with the system size, which means that as long as we consider a linear number of polymers, which we do because of the screening that I explained earlier, we scale linearly with the system size. And if the energies look scary, the gradients are much more complicated, but they still scale quintically. Okay, so this is last of my more technical slides for if there is some expert in the audience. To let you understand the challenges, many of these quantum chemistry calculations arise from the need of evaluating these force-center repulsion integrals, so which are 6-dimensional integrals of 4 Gaussians placed at different atomic centers. We have to compute order n to the 4th of them, so you cannot store them. Furthermore, the calculation is complex, being handled in batches with different computational workloads, which depend on the nature of these 4 different functions. So this leads to a potential workload imbalance and complex recursive algorithms that are memory bound or with low flop rates. So they do not run fast and efficiently enough on GPUs. For example, the bottleneck of HashiFock, which you need to run before you can get to the MP2 level, is forming these integrals in batches and combining them on the fly with the density matrix D there on the slide to obtain a Fock matrix elements F. Now, to save on the huge amount of these integrals that we have to compute, symmetries are used where you can permute the indices of these 4 standard integrals or a 4th order tensor and obtain the same number. However, while that saves on the integrals, this leads to the fact that each one of these elements can contribute up to 6 blocks in the Fock matrix, which leads to scattered memory access patterns, and we're running parallel to race conditions, so a need for further synchronization, which lowers computational efficiency. To eliminate these performance problems, we devised a new technique that uses the so-called resolution of the identity approximation. What this does is to take these 4th order tensors and accurately approximate them as a sum of products of 3rd order and 2nd order tensors. It's a very accurate low rank approximation. This means that we can compute on GPU only order n cubed integrals. Now we can store them on the host end or on the GPU. And once done, this Fock matrix build can be implemented using linear algebra routines such as BLAS, and specifically the bottlenecks become matrix multiplications or in double precision, which run very efficiently on GPUs. The same applies to the MP2 component, and we can reuse synergistically some tensors between HashiFock and MP2, so we can run pretty much all the time these double precision matrix multiplications to maintain very high flop efficiency. Some performance numbers, the traditional Fock build in excess is already 30 to 45 times faster and 12 to 18 times more energy efficient than all the CPU state-of-the-art codes. For small to medium molecules, when we apply the array technique on top, we obtain a speed up of 2 times on top of our own code, so we are compounding that speed up. The array MP2 component for energy and gradients is 95 times faster than CPU state-of-the-art code and 19 times more energy efficient. Now, these results did not use the fragmentation technique that I discussed earlier. When we use this fragmentation technique, we become faster and faster, as you see on the blue curve there, because of the lower scaling. And finally, we assessed the error. So we computed the gradients and energies with and without fragmentation. The RMSD of the gradient error is of the order of 10 to the minus 6, which is below the threshold of geometry optimizers in the field. What that means is that the error, it cannot be in practice observed from a computational perspective. And that ensures also that we conserve energy if you run an MVE for a calculation, for example, in ensemble calculation. Along our pathway of enabling these capabilities, we have been able to use a scale the entirety of the top 1 machine in the world systematically, submit first and then frontier, to push the boundary of applicability of accurate ab initio wave function-based calculations, with results published in a C20, 21, 22, and 24. In 23, we took a break, planning for AIMD, this ab initio molecular dynamics, and this led my group together with QDX Technologies to rewrite the entire code base, as you do. And this was because AMD had very different requirements in terms of program efficiency. And then last year, as Georgina has mentioned, this led to the largest and fastest ab initio molecular dynamics simulator at the MP2 level, which was awarded the ACM Gordon Bell Prize. At that stage, we had the array technology, and our question became, can we run on these big machines here on the slide for portability and enable for the first time AIMD simulations of biosystems at the MP2 level. This was especially ambitious given the largest prior calculation was done on 140 water molecules. So to evaluate the feasibility of this challenge, we benchmarked the latency of a single AIMD time step, so a single molecular dynamics simulation time step using our RIHF plus RIMP2 approach against state-of-the-art quantum chemistry codes. And as you can see in the red box, even when using a single node of GPUs, so 4 GPUs, we are pretty much 3 orders of magnitude faster than state-of-the-art code. Then when we move from 14 to 16, we keep lowering our latency, but from 16 GPUs to 75,000 GCDs on Frontier, that's completely another game and requires a more sophisticated approach. And here I show just the elements of this complicated algorithm. I have already mentioned molecular fragmentation. We lower the scaling, we increase the parallelism. Then we have a multi-layer distributed GPU memory and workload manager that does 2 main things. The first one is to allocate and pin all the memory, host and GPU memory across the whole machine, because we can reuse that. You don't want in a molecular dynamics simulation at each time step trying to allocate or pin memory because it's synchronizing and it's very expensive. Besides that, it has a very lightweight workload distribution management system where we can distribute these polymers across an entire system and across the nodes, within the nodes, across the GPUs very, very quickly. We have designed a new algorithm that enables us to do a synchronous time step. What this does is to eliminate the synchronization barrier at the end of each time step in ab initio molecular dynamics. I mentioned already the RIHF plus RIMP2 technique that enables us to recast the bottlenecks in flop-efficient matrix multiplications. And then building on that, we built our own runtime auto-tuning system to run these matrix multiplications optimally at runtime. So I will explain a bit more about 3 and 5, then we move to results and then the AI section. To update the positions in AIMD, we require forces which are calculated on the various fragments, and you imagine each fragment is calculated on a different GPU. At the end of each time step, you have to gather the forces from all these fragments across a machine with 75,000 GPUs. This is a massive synchronization event, which is very inefficient. However, in these fragmentation approaches, all polymers are formed from the monomers. And for this reason, the position of the whole molecule requires you to update only the monomers, and then you can form the polymers from them. Now, the position of each monomer here depend only on the polymers that are significant based on the radial cutoff that I explained earlier. So if you look at the slide, the position of monomer 1 here, which is the pink one, depends only on the polymers on the slide, which do not include the monomer 4 because it's beyond the radial cutoff. So there is no dependency on that one. So what we do here is to use an asynchronous time step algorithm that exploits this fact and enables us to move monomers at the next time step as soon as all their dependencies are satisfied. This way, we can form all polymers at each time step from the monomers which are moved at that time step and continuous distribute calculation to the GPUs. In other words, this allows us to exploit the parallelism across time step, so across time, and to keep the GPUs busy literally all the time running these fragment calculations. For example, we're running our AIMD on this system with 5,500 electrons on 4,098 A100 GPUs. This technique gives us a 40% speed up only by doing asynchronous time steps. Last piece is this runtime auto-tuning system. And this is quite broad and general in computational science. You will have this problem if you run, for example, on MI250X on AMD. To understand the need for this RTAT, the bar chart on the left shows the flop rate of the same matrix multiplication. So we have the same matrix sizes, okay, and the same elements in the matrices obtained using 8 different strategies. In strategy 1, we obtain C by doing A transpose times B. For those who know BLAS, what that means is that you set a flag in your function call and do the transpose. In strategy 2 instead, we do the transpose ourselves first and feed to BLAS A transpose and then multiply it by B. Now there are 8 of these, and as you can see on the slide, they give different performance in terms of the flop rate. To maximize performance, we seek to find the optimal strategy between these 8 at runtime. And this is exactly what RTAT does. As we run our AIMD, RTAT runs all the matrix multiplications using different configurations until it finds the optimal one. It remembers it, and it sticks with it. This is perfect for AIMD because at each time step, we have to run matrix multiplication with the same sizes, so we are bound to find the optimal strategy. And here, as you can see in the bar chart, we're able to gain very significant speed ups up to 34% by using RTAT for matrix multiplications. Performance results, weak scaling results here were obtained on Frontier and Perlmutter using crystal lattice structures of paracetamol, ibuprofen, and urea. Note that the plot here shows the weak speed up in terms of percentages of double precision peak performance for each node count. So in other words, the plot shows a nearly ideal weak parallel scaling, obtaining systematically around 60% of double precision peak performance on Frontier, going up to roughly half of the machine. Now, strong scaling, nearly ideal, going this time up to 9,400 nodes and 37,600 GPUs, or double that number in terms of GCDs. Obviously, we need to provide the larger and larger molecular systems to avoid the workload imbalance coming from resource underutilization. That's why you see those molecules on Frontier being larger and larger as we use more nodes. If your molecule is not big enough, you do not have enough polymers to keep all the GPUs busy. With the largest system here having 232,000 atoms, we had already broken for the first time the million electron barrier at the MP2 level in energies, gradients, and AIMD simulations. Now a mix of parallel scalability and flop performance. This was done on the Alps system in Switzerland, which has GH200 superchips. Flop here accounted by accounting only for matrix multiplications, which actually underestimates the flop count, and dividing by the whole program execution time, which contains many different algorithmic patterns because it's an AIMD simulation. Once again, the percentages are not parallel efficiencies, but percentages of FP64, so double precision RPIC. Achieving 81.5% of double precision on 4096 GH200 is still unprecedented for any scientific application. Third dimension, time step latency. How fast is the time step here? And here we ran our AMD applying it to an alpha-beta amyloid fibril system called 2BEG to simulate the folding and misfolding of these amyloid fibrils, which is a hallmark of Alzheimer's pathology. Force fields have consistently failed to capture misfolding dynamics of these fibrils due to the fact that they are driven by non-covalent interactions. As I mentioned earlier, this is where force fields and hybrid DFT fail. The system here includes 1.5 thousand atoms and 5.5 thousand electrons. The plot at the top shows how nicely energy is conserved during the simulation, fully validating the correctness. In our Gordon Bell submission, we had this time step latency on Perlmutter of 3.4 seconds on 4096 A100 GPUs, which was already more than 3 orders of magnitude faster than the state-of-the-art. We don't know how much more because that's a lower bound. It's probably significantly more. However, when accessing ALPS on the GH200, we obtained this amazing latency of 1 second per time step, which at this level of accuracy is a major achievement in AIMD. Last test, we went for record performance. Here, our calculation tested whether we could predict the correct lowest energy polymorphic form of various crystals. Polymorphs are different crystalline arrangements, and they are very important in drug discovery, as different polymorphic forms have different properties and toxicity. There's a very famous case, which is that of ritonavir, which had to be withdrawn from the market because the wrong polymorphic form was predicted. In any case, different polymorphs differ typically for a tiny amount of energy, and they require very large molecular models. In this case, our largest polymorphic crystal contained 510,000 atoms, over 2 million electrons. This was over 1,000 times larger than any ab initio molecular dynamics calculation attempted at the MP2 level. And on this calculation, using 9,400 nodes on Frontier, we obtained a performance of over 1 exaflop, full in double precision, breaking for the first time the double precision exaflop barrier for a scientific application. There are many other capabilities in excess. This is just to say that this program is currently being deployed on the major HPC platforms in the world. It's not yet available. The first one will be the POSI Supercomputing Center, which is going to deploy it probably within a few weeks. Now, what do we do with that in terms of drug discovery? Well, I don't have the time to show the possibilities. Well, one possibility is that you retain a certain component of the original virtual screening pipeline and then feed the results to these high-performance quantum modeling simulations. And what you would expect at that point is that you should obtain a better correlation with experiments when you measure the binding affinities. Does that work? Well, there are some details of the calculations that you can look there if you're an expert, but the idea here is that we run this technique for CDK2, which is a drug target, a very common target. Each point on the plot shows a ligand and the binding affinity for that ligand compared to experiments. And each one of these calculations on 4V100 takes about 15 minutes. And we obtain a nearly perfect correlation, in this case, between predicted and experimental binding affinities. Moving on, what about AI? What's the role that AI plays into this? Well, first of all, AI can be used to further accelerate these simulations. These days do exist machine-learned force fields that they trying to mimic the quantum interactions by using neural networks. So your molecular system here is partially or entirely modeled using a neural network trained on quantum mechanically accurate data. So they give you the potential energy surface if you want. You move the atoms around, you measure the energy, and then by backpropagating, you can obtain the gradients, which means that you can also simulate, do molecular dynamics. Main advantage is obviously that this is faster, is orders of magnitude faster than whatever quantum simulation, even our own code. And so you can run, in principle, more compounds, more frames, larger systems. Main disadvantage, typically, well, in general, lower accuracy than quantum. Second, unreliability. As any AI and machine learning model go sufficiently outside the training set, it will fail. AI models typically do not extrapolate, and this is a problem for molecular dynamics where intrinsically you're trying to explore different conformations. One other way to say this is that it's well known that in chemistry, you have this lack of reliability, and probably one of the main sources is the lack of accurate data, reference data, training data, right? And obviously, your model can be as accurate as the data that you feed it, and in chemistry, there is so much variability that it's very difficult to obtain sufficient and sufficiently accurate data to train these models. Second issue, many, if not all, of these neural network force fields use an incorrect, physically incorrect functional form. They compute the energy as a sum of atomic energies, where each atom energy is a neural network, And each atom energy is computed for that atom, accounting only for a radial cutoff of the atoms around. So if you go beyond that cutoff, that atom doesn't see the other atoms. Now, the issue here is that quantum mechanical energies are not atom-wise additive. They are not even pairwise additive. They are many-body effects. So this approach works only reasonably well for small molecules based on this radial cutoff. One way around this is to combine, it is what we do at QDX, fragmentation with delta machine learning. The idea here is, instead of taking a big network and trying to simulate the whole system with that one, what we do is to break it into fragments as before. And now we have different networks. Each one computes the monomers, and then the dimer correction, and then the trimer corrections. Now, the big advantage of this is that there are many advantages, I guess. One is that dimer and trimer corrections are quite small, so they are much more forgiving in terms of accuracy than metrics that compute the energy of the whole system. Second, your training set, you just have to train on fragments here. So you can imagine how this is culling the amount of data that you need to produce, because you don't need to produce many configurations for an entire system where you have this combinatorial explosion. You have to do it only on the fragments. Quickly, some results there. This is just an initial test that was done on 11,000 test data points. The metrics for training, validation, and test are there. This was trained to obtain the MP2 energy, and we have 95% of the predictions which are within 2 kilojoules per mole, which is basically experimental accuracy. So what do we do with that? How can we leverage these to further accelerate our quantum accurate simulations, but also making sure that they remain accurate? Well, all our simulations so far evaluated the polymers using MP2, all of them. So very high, very intense calculation on all these polymers. Large time savings can be obtained virtually with no loss of accuracy if you treat interactions between close fragments with high levels of theory. So very expensive, but quantum levels of theory, and distant ones with lower levels of theory, which are significantly cheaper. You do not lose accuracy. Why? Because quantum effects are short range. So the idea here is then, can we use this idea to develop an adaptive hybrid quantum and AIMD simulator where fragments are treated either quantum mechanically or using, in this case, Bayesian neural network force fields trained on quantum accurate data based on prediction uncertainty. And the example is there on the slide. Imagine you have this fragment, you run a Bayesian neural network force field. What this does is to give you the forces, but also give you a measure of uncertainty. If uncertainty is high, you revert back to the quantum calculation. Otherwise, you retain the Bayesian neural network force field force estimate. And then you can use the data that you obtained with the quantum to retrain your Bayesian neural network force field. So what we are doing here is to produce data on the fly when needed and where needed. Last example of AI. Remember earlier I said at some point we have some lead compounds, we give them to the medicinal chemists and they start tweaking them, and this takes years. At QDX, we do this largely using artificial intelligence. So at this point in the pipeline, you have a scaffold and that you don't want to change. It's called the pharmacophore model. And there's all the interactions, most of the interactions that you want to see, you just need to optimize. So you add the pieces to this molecule to trying to optimize for certain properties. It might be affinity, it might be don't want to be toxic, it might be bioavailability, all these kind of things. So the idea here, and we are definitely not the only one to do this, is to take these scaffolds, and what we do is use an encoder to encode them in the latent space, and then in that latent space we can do an optimization using latent space variables. What do we optimize for? Whatever you want. Again, binding affinity, bioavailability, etc. Once you optimize, then you can decode that vector into your actual structure. And you can reiterate this until you are satisfied with the process. Our big advantage is obviously that our objective function is a quantum function with simulations, but this works in principle more in general. The idea here is that you are not limited by human bias, ability, or creativity. It can be constrained. In fact, our own is constrained to yield the synthesizable molecules. And supports the different objective functions, as I mentioned, is obviously faster, cheaper, fully automatable. You can run it the whole day if you want. Okay, so looking at the future, now that we have this chemical simulation and generation technology, as we perfect it, we envision its integration in an automated chemical discovery framework that combines high-performance computing, quantum chemistry, machine learning, and one element, which is robotics, to discover and optimize chemical structures for targeted chemical properties, such as desired therapeutic efficacy in drug design or improved catalytic properties for sustainable energy applications. Now, let's look at one implementation of these. If you apply this paradigm to drug discovery, on the left, we retain the original initial virtual screening capabilities. Then we can feed thousands of pre-screened candidates to our high-performance hybrid AI quantum simulator. This can support more calculations now because of the AI acceleration to simulate the binding with near in vitro accuracy. Then we can take our candidates, the best ones, and send them to an automated pipeline for synthesis and in vitro testing. This is a self-driving lab that can use AI and robotics to perform automatic synthesis and characterization, including quantitative activity relationship studies, which can be done, again, with machine learning models. Then we send these structures to our best binders to a unit for design and optimization of our compounds, which is no more human-led, but it is rather AI-led. And this uses generative AI, as already possible and shown earlier, to propose modifications to existing scaffolds and structures for optimizing them. Then we iterate this cycle. However, this is now fully automated. In fact, this can be thought of as a combination of a virtual self-driving lab together with a physical self-driving lab. This framework here that I call the matter transformation automaton is a digital chemical discovery platform that can accurately and continuously propose new therapeutics, new materials, and chemicals with a minimum amount of automated physical experimentation and little or no human intervention, ideally running 24 hours a day, 7 days a week. And that takes me to my conclusions. The breakthroughs that I've shared today, scaling quantum accurate calculation to the bioscale, integrating AI for automation and molecular structure generation, are more than just technical milestones. They represent the fundament of a big shift on how we conduct molecular discovery. For the first time, we can perform quantum accurate calculations at the biomolecular scale. I've shown you the speed, the scale, the predictive power, and the validation with experiments of these calculations. These capabilities are transforming drug discovery through QDX, for example, with the potential to directly impact critical challenges in the field, such as Alzheimer's. Looking forward, the future of scientific discovery will not be as bound by experimentation and by the latency of human operation. We are laying the groundwork for an autonomous matter transformation platform where we combine HPC, quantum mechanics, AI, and robotics to design, synthesize, and validate new materials and drugs on demand. So this is not just about computational chemistry or HPC. This is about redefining the way we innovate and discover in molecular sciences to address some of the outstanding challenges today. And with that, I will thank all the people that have participated in these, my PhD students and QDX technologies, and I will be happy to take any questions.
Thanks, Giuseppe. Really impressive talk, particularly the performance, reaching exascale flop. Really impressive. And I was wondering, because the size of the problem is so humongous. With, if I understood well, of the order of 10 to the power 5 atoms, and and all the interactions between the atoms, many body problems. I was wondering how the computation cost and execution time would compare or compares against an experiment where you would actually measure directly the energy levels using maybe a spectroscopy. I'm not really a specialist at all. And if, because in some fields, we don't have actually the luxury to have an experiment. For instance, in climate simulation, we can't just perturb the Earth's climate and see what happens. But yeah, do you have anything to comment regarding that?
Yeah, absolutely. So in terms of the applications, obviously for the largest systems, when you're using an exascale machine, you want to make sure that your problem is a high impact problem, and in general, some of these problems, or many of them, as I commented originally, you might not even have necessarily experimental characterization techniques, so there's no alternative. Second point, for drug discovery, you have seen that I've shown scales of hundreds of thousands of atoms. Systems in drug discovery contain between 2,000 and 6,000 atoms. We run these on 4 GPUs, V100 GPUs. And one of the key things of QDX technologies is that the cost is significantly lower than running a binding affinity experiment. Binding affinity experiment costs between $200 and even $2,000, depending on the quality of the assay. Our calculations cost between $5 and $7.
I was wondering how you look at the future of this. So considering the developments in GPU hardware, where I think floating point 64 doesn't get quite as much attention as lower precision floating point because of the very AI-driven developments, and looking at what you said, that you basically use floating point 64 and you have difficulties, but approaches by difficulties with AI-driven models. So will this be a problem, or are you at a level where it's already good enough for what you need, or are you hoping for quantum computing coming to the rescue, or how do you look at this?
No, I'm not looking at quantum computing in this area. Well, it depends on where you're applying it. I will make a short comment on that. I don't think that's something that probably not even in 15 years you will get the latency of a quantum processor to be able to run thousands of these or millions of these calculations at that scale. That being said, it will solve other problems, even in drug discovery. So for example, quantum machine learning and multi-factor optimization problems. From the perspective of FP64, I've been wrestling, of course, with AMD and NVIDIA. So the idea is probably, in some cases, this might be emulated, but what we are doing currently is obviously they're kind of making it slightly more difficult for us, but is to look at mixed precision, obviously. I believe the community needs to be very, very careful with accuracy, especially when we are simulating these things. I see all the times single precision, when you're simulating systems which are at a certain size, you lose an enormous amount of accuracy, and chemistry is made of differences of energies. So it does matter a lot. So it will be about designing the calculations in a way that you're minimizing your floating point error and using mixed precision in a smart way so that you can retain the level of accuracy.
Oh, there's so many. It's fabulous.
Thank you. Wow. As an educator, I just want to compliment you on a fantastic presentation in terms of its clarity and insightfulness. It's brilliant.
Thank you.
As a chemist, I've faced this thing of feeling inadequate, and I'm sorry we can't give you more data, but we measure bulk properties of large numbers of molecules and not the detail at one level. But I do have a couple of questions. As you look at the variations of your outputs for the different fragments as they increase in size, is there any value in analysing that in terms of getting insights into the nature and detail of secondary and tertiary interactions at greater distance? I mean, is there extra scientific value in the numbers that you're getting out in the middle of your calculations that might be exploitable? So that's one question. The second one is whether you've looked at applying this kind of thing to phase boundaries and interfaces. I mean, some of the really interesting parts of catalysis and so on, of what's going on in the layers around surfaces and so on, seems to me you've got scope for doing that here, and I wondered the degree to which you had started to examine that problem, which is a completely separate one from the pharmaceutical one, but arguably a bigger one in terms of the future of the planet.
Yes. Okay, I'll comment on the first one first. Yes, the interactions at the dimers and trimers. So dimer interactions, pairwise interactions, there's a component, to some extent you can even approximate them classically. Obviously they are not as accurate. Trimers interactions are purely quantum. And they do give a lot of insight on actually the various interactions, and we use them, for example, in QDX for the design on novel therapeutics, because they give us information on if we swap some chemical groups within the molecule, how the interaction is changing, how the stability is changing, etc. This applies also to proteins. So, and the machine learning models that you have seen, training directly on the dimers and trimers is pretty much what you're mentioning. So the idea is all the information is pretty much contained in there. You don't need to look at the big system, you need to look at pieces of the system combined together in a many-body way. And that the results show that this is an accurate way of dealing with that problem. Obviously, you might wonder for other systems like materials, how do you do this? That's not my application at the moment. I'm looking at biosystems. I'd rather solve one problem first and then think about another problem. Interfaces is something that we actually started with interfaces. They are very interesting. Once again, it is a big problem. And yes, in this case, there is definitely scope for applying this technology to that. Will QDX do it or my research group do it? At the moment, we don't have headspace for it. It's just, there's enough work at the moment, but definitely it is a huge application. And as mentioned also there, for interfaces, force fields are not there. So definitely a combination of quantum and machine learning will give much more accurate results.
Thank you. That was a very inspirational talk. I'm actually really interested in the last bit that you touched on about fully automated labs. That really captures the imagination. And there's various kinds of automation that tend to enable smaller, less resourced places to get into kind of high-tech manufacturing. How do you envisage this? Do you think this is something that we would be able to do here in New Zealand where we're not as resourced, let's say, like NIH and scales like that?
Yeah, so one example of a researcher, well, of a country that has partially enabled these with terms of robotic is the Acceleration Consortium in Canada. They have part of that. They have the self-driving physical lab, which probably is the most expensive one. So we are building the self-driving virtual component at the moment, and we are currently in conversation Melbourne with various institutions to actually enable the whole self-driving lab, completely dedicated to drug discovery. You need to fund these things, obviously, and it's also a noble cause. You know, I'm pretty sure that we will get to a point where we can design some new therapeutics for currently very challenging diseases. In New Zealand, I am not sure precisely what is the landscape, but obviously it requires sufficient funding, but also the expertise. And that is, besides the funding, a big problem in this area, right? We are moving to a very multidisciplinary scientific landscape, and we will need the people that are able, in terms of the skills, to go across AI, quantum, and biology. That's a challenge for us as well. So there is training, funding, and then putting the pieces together. Certainly, the digital component here, as you can see, is very important, if not crucial.